Hydrolysis and buffers lab. So we figured out how much of the solid we needed to weigh out to make 25 mils of 0.1 molar, and we measured the pH. We know that, for example, ammonium chloride is going to have a pH, probably less than 6, 5 something is fairly standard. I'm going to leave you to use your values that you got here. When you write the hydrolysis reactions, it is very important to do two things. One, dissociate the salt into its cation and anion. So if I have ammonium chloride, I'm not going to react ammonium chloride. I'm going to take and recognize that I have ammonium and I have chloride. Chloride, we know chloride is inert. When we looked at our salts back from chapter 16, we remember here, it's really important to have this list in your head. Remember that the conjugates of the strongs are inert. So if you have your strongs memorized, and you need to have these memorized, you look at your HCl, HBr, HI, HNO3, HClO3, HClO4. And those are our strong acids. Our strong bases would be our group 1, and these would be like sodium, potassium, lithium, etc., hydroxides. And then we have the 3 of the group 2 hydroxides that are also soluble, are calcium, strontium, and our barium hydroxide. And these guys are all going to dissociate in water. In the case of the acids, they're going to ionize in water. And the key here is that these are our strongs. And remember, the stronger the acid, the weaker the conjugate base. So if we have a strong acid, and remember our strong here is going to have an undefined K, we have so little of the original left as to be considered to be 0, giving us our K that is undefined. If these are our strongs, our conjugates are inert. Inert meaning do not have any acid-base properties, do not react with water, and those are chloride, bromide, iodide, nitrate, chlorate, and perchlorate. I have left sulfuric acid off of this because it's going to more complicated. The first step only is strong, as well as our group 1 cations, and you can put the whole list in there. We just don't tend to have them in the lab. And then, of course, calcium, strontium, and barium. Why is this relevant? This is relevant because anytime you see something like ammonium chloride, you recognize this as the conjugate base of hydrochloric acid, which means it is inert. And because it is inert and it does not react with water, the only thing that matters is ammonium. So what I'm going to do here is I'm going to dissociate, ignore the inert species, and instead of starting with ammonium chloride, I'm going to start with ammonium. And I'm going to write my hydrolysis reaction as ammonium reacting with water, making ammonia. This is liquid here, plus hydroxide, hydronium, turn my brain on. With the note, not only is mass conserved in a reaction, charge is also conserved. So if you look at this, we have +1 on the reactant side. We also have +1 on the product side. When you do these, make 100% certain that you do not lose the charges. If it's an anion, it's going to be negative. If it's a cation, it's going to be positive. We have made hydronium, which is important because that's consistent with a pH that's going to be less than 7. Make sure you do that with all of them. Recognize that when we go here to this next question, I'm going to ignore my dissociation here or my buffers for a second. And we're going to ask you calculate the pH of sodium bicarbonate. Bicarbonate is amphoteric, meaning it can be both an acid or a base. So let's think about what that means. If it is an acid, we're going to react it with water, and we're going to, remember, it's a proton donor, and we're going to make carbonate plus hydronium. If it's a base, it's going to react with water. It is going to make carbonic acid plus hydroxide. Now, it is your job from your data to figure out which one it is doing. Okay, and you're going to be able to tell that from your pH. So I'll let you look at your pHs and determine which one you have with a note on which K do you use. If we're looking at it and we're thinking about it as an acid, if we think that this is the correct reaction, we're removing the second proton. This is the second proton, and you would use Ka2 if it's an acid. But if we're looking here as a base, anytime we're given Ks for an acid, but it's acting as a base, we know that we have to calculate our Kb. And we're going to do that by recognizing that if we have our conjugate pairs, carbonic acid and HCO3 minus, if this is our acid and this is our conjugate base, such that Ka for our acid multiplied by Kb for our conjugate base is equal to Kw. If we're assuming it is an acid here, or excuse me, we're assuming it's a base, and this would be the base and its conjugate acid. And we could do this as well. Remember that conjugates just mean that they're pairs. And so I could write this instead as a base and a conjugate acid. Doesn't make any difference either way. But the key here is that if you are working with the idea that bicarbonate is a base, you are going to have to calculate Kb. And to do that, because this is the acid portion, you are going to use Ka1 to calculate Kb if it is a base. If we're assuming that bicarbonate is acting as a base rather than the acid, you're going to be able to tell that from your pH, so make sure you use the right one. And then, of course, calculate your percent error. To look up the pH, so you're going to look up the K, and you're going to calculate what the pH should be of your buffer solution. And then you're going to do it after you add some sodium hydroxide. I've already posted the video on how you do this, so take a look at the buffers and titrations or the buffers video that I posted, and you'll be able to see how to do that one from there.